we know how to find a Taylor series, and we also know how to find its interval convergence. The one thing that we haven't done yet is to show that when the Taylor series converges, that it actually converges to the function that it represents on that interval convergence. So that's what we want to look at is, will the Taylor series converge to the actual function's value on the interval convergence? So have to go back to what does it mean to converge? So we've got our Taylor series, and I'm going to represent that by the form f of x. Now the function f of x could be written as the Taylor polynomial, which is the piece of n of x, plus that remainder. Remember, the remainder was the rest of the part that wasn't included in the polynomial for the Taylor series. So anything else that's not already in this, so it's just going to be the function f minus that piece of n. So this was the remainder. Now, in order for a Taylor series to converge, that means that this remainder needs to go to 0. So the limit of the remainder term must be 0 in order for this function, the Taylor series, to converge to f. Okay, now the formula, though, we saw this previously, for this remainder is it's going to be the n plus first order derivative evaluated at some c, and that c is some number in between the x and the a, over the n plus 1 factorial times the x minus a to the n plus 1. Remember that n plus first term that gave us that upper bound on what that error was going to be. And that's what this form is going to look like, except that we had to get us just that any c in that interval is how we use the mean value theorem to actually write it in this form. So let's look at some series that we just came up with and determine if they actually do converge to that function. So we need to show that this remainder has a limit of 0. Okay, we've already talked about the Maclaurin series for f of x equal to e to the x. Okay, and I'm going to use the remainder, r sub n, the n plus first order derivative evaluated at some c times the x minus a, which we're looking at a being 0 in this case, so the x to the nth power, or n plus 1 power, over the n plus 1 factorial. And c is just something that's in between the a and the x. So c is something in between 0 and x. Okay, so now we got the Maclaurin series for the e to the x. The Maclaurin series was just the x to the n over the n factorial, and n went from 0 to infinity. Okay, so let's see what that expression, that remainder, looks like. We know the remainder, r sub n, will be less than or equal to the nth order derivative of the function. Now the nth order derivative, remember, for f of x equal e to the x, the nth order derivative will just be e to the x. So the nth order derivative evaluated at c then will be just the e to the c power. And then we're going to have the x to the n plus 1 over the n plus 1 factorial. And I want to look at that limit, the limit of the r sub n's as n goes to infinity. So we've got the limit of the e to the c, x to the n plus 1 over n plus 1 factorial. And here the limit is as n goes to infinity. Okay, now e to the c, I need to have some sort of a bound on that or be able to compare it to these other expressions. What I want to do is I want to note that the e to the c, since c is less than x, e to the c is going to have to be less than e to the absolute value of x. Now, I don't know if the x is positive or negative, so I guess this was really just if the x was positive. So the c had to be somewhere between negative x and x. Depends on whether c was positive or negative. So now, we know e to the c is less than e to the absolute value of x. So I can rewrite this expression then will be less than or equal to the limit of e to the absolute value of x and then x to the n plus 1 over n plus 1 factorial. And this is as n goes to infinity. Now, e to the x doesn't have the n in it, so I'm going to pull that out of the limit, and now I just want the limit of x to the n plus 1 over n plus 1 factorial. And I need to find that limit as n goes to infinity. Now, if you remember that growth table that we've talked about in the past, we had that x to a power grew more slowly than the x factorial, the n factorial. Okay. X is a number, so x to the n is just going to be your exponential function, and it grows slower than that factorial does. So this limit then has a value of 0. So e to the x is fixed for some specific x, and this limit will be equal to 0. Okay, so what that means then is that if the remainder converges, has a limit of 0, then that means that this infinite series is converging to the function. Okay, because we found the remainder, the difference between the function and that Taylor polynomial, which is the beginning of this Taylor series. So this concludes then that this Taylor series, not only does it converge in the interval convergence, but it also converges to the function f of x. So on its interval convergence, which is minus infinity to infinity, it will have the value it's converging to is the value of the function for that particular x. Okay, so now let's look at another one. Let's look at cosine of x. We got the Maclaurin series, had just those even terms. Now I want to look at the remainder. I'll know the function f is what this infinite series converges to if the remainder has a limit of 0. So the limit as n goes to infinity of r sub n, and that expression is the n plus first order derivative at some c times the x to the n plus 1 power to the n plus 1 over the n plus 1 factorial. That's the limit as n goes to infinity. Now let's look at the order derivatives for cosine of x. We knew that f of x was cosine, f prime of x was negative sine, f double prime of x was negative cosine, f triple prime of x is negative sine, so back to sine, and then the fourth order derivative of x is back to cosine of x. So we're repeating these four values over and over. So we're not sure which of those it will be, since we don't know exactly which derivative it's going to be. But one thing we do know is we know no matter what the x value is, this expression is always less than or equal to 1. So I'm just going to say that this is less than or equal to the limit of 1 times x to the n plus 1 over n plus 1 factorial. And now for the same reason before, we know that the function x to the n grows more slowly than n factorial, since this would be some fixed number raised to the nth power. And that means then that the limit of the smaller of the two must be equal to 0. So this limit is equal to 0, which then, if the remainder has a limit of 0, that means that that series, negative 1 to the k, x to the 2k over 2k factorial, converges to whatever that function's value is on its interval of convergence. And that interval of convergence was minus infinity to infinity. So for all x, whatever this infinite sum converges to, it will be the function's value, the value of cosine of x. So that's why we can say then that this infinite series is cosine of x, because it does converge to it. Okay, this next slide just has a bunch of the known power series, Maclaurin-Taylor series for just the basic functions. We've got 1 over 1 minus x, 1 over 1 plus x, e to the x, sine of x, cosine of x. Okay, natural log of 1 plus x. So you can refer to these and use them, for homework. They will be provided to you on a test. Don't worry about this last one. I didn't cover the binomial expansion. But these are some known ones that, unless you're specifically asked to develop it, you can refer to this and use it. So if you're trying to form new ones using compositions or multiplying by power of x, then you can go ahead and just use this instead of having to develop it from scratch.